Yeah, I think we can get started.
Okay, go ahead.
Hey, good afternoon, everyone. Thanks for joining us. My name is Franco Montalto. I'm a professor of civil architectural and environmental engineering here at Drexel University, and we are happy to introduce this webinar series entitled Adapting Stormwater Management for a Changing Climate. And this first webinar is given by Mark Maimoni, who I'll introduce in a moment. The title of this presentation is Transforming Daily Global Climate Model Precipitation Output for Use in Hydraulic and Hydrologic Modeling. A word on, where's this slide? Okay, this webinar is part of a series being organized by CC Run, the Consortium for Climate Risks in the Urban Northeast. We are a consortium of 5 universities funded by NOAA to conduct stakeholder-driven research focusing on the climate change impacts in the urban corridor spanning approximately from Philadelphia up to Boston, but working with our neighbors to the south, MRISA, which is the Mid-Atlantic RISA. And we do a lot of these types of stakeholder engaged research and are happy to bring you this particular series. The webinars, the 4 webinars, which I'll give you a review of in a moment, are the preamble to an actual workshop to be held in Washington, D.C. on March 5th and March 6th, during which we will synthesize for stormwater, wastewater utilities, practicing engineers, and others, what we've learned through the webinars. And the focus of the overall workshop is helping water utilities and those involved in the planning of water infrastructure to take what we know about changes in precipitation, for example, from global circulation models, and to incorporate that into the types of products that are used in stormwater and water planning, urban water planning and flood control. So focusing on time series, focusing on IDF curves, focusing on design storms. The idea is to take the big picture predictions of extreme precipitation and bring them down to a scale that we can actually use them in decision making. So we've got 4 webinars planned for you, kicked off today by Mark Maimoni. Mark will also do next week's webinar. And then we have Ziwen Yu and Eric Rosenberg and Art DiGaetano coming up in February. And for those of you who happen to be professional engineers in Pennsylvania and New York, you can get PDH credits for your attendance at these webinars. And if you're able to join us for the actual workshop in person in Washington, D.C. for that event as well, we've got continuing education credits pending for other states. So please send us your information in the chat window and we can give you a certificate of completion. So today's speaker is Mark Maimoni. Mark Maimoni is a water resource engineer at CDM Smith. His academic background includes a BS in civil engineering from the University of Technology in Delft, master's in environmental regional planning, and a PhD in water resource planning from the University of Groningen. Mark's got over 30 years of experience in groundwater and surface water management, water quality studies, urban water management, mathematical modeling, and has published extensively on water resource management as well as climate change and decision support science. And Mark's been very active in Philadelphia, helping to make the Philadelphia Water Department to develop their climate change adaptation program as well as their stormwater plan, the Green Cities Clean Waters program. So with that, I will stop sharing and turn the presentation over to Mark.
Before Mark starts, I just want to orient everyone in case you haven't been on a Zoom webinar before. This is Corinne. I'm also from Drexel. And so at the bottom of your screen, you'll see there's a Q&A box as well as a chat box. If you have any questions, you can type them into the Q&A and those will come to us. Or at the end of the webinar, when it's the Q&A time. If you want to click the raise your hand button, I can unmute you if you want to ask your question verbally. So either the Q&A or the raise button hand will indicate that either you have a question or that you would like to ask your question. Thanks. And yeah, Mark, I'll hand it over to you.
All right, thank you very much. Welcome, everyone. I just want to acknowledge, like anything in engineering these days, you never do anything alone. Julia Rockwell heads up the Climate Change Adaptation Program at the Philadelphia Water Department. And Sebastian Malter, who was with the Philadelphia Water Department, now he is with CDM Smith, did a lot of work with me on this and certainly should be fully acknowledged as one of the authors of what I'm going to present today. Just some context. The Philadelphia Water Department started a climate change adaptation program about 5 years ago. And there are a whole number of phases. I'm just going to focus on the phases that are relevant for today here, where they started out with trying to figure out what they have and what they need in terms of climate change information. Then moving on to see what the climate models could tell us about the Philadelphia region and whether they perform well enough for us to use the information or the output. And then how do we adjust observed precipitation data to make projections of climate change for future. And all of this is about urban stormwater, which means that we need hydrologic and hydraulic models of collection systems in order to examine storm influences on flooding and the collection system itself. So these models run on fairly short time steps, and you'll see that is what this is all about. Global climate model output is readily available at this website. It's the Bureau of Reclamation, but all of these institutions participate in making this available. It's downloadable. It's on a daily scale. There are various projections from the prior CMIP projections and the most recent. And of course, we're up for an update in about 2 years or a year and a half, and there'll be more projections available. So these are downloadable, and that's exactly what we have used. They do have a number of types of downloads. Basically, these are coming from the global climate models. So they're actually modeling the entire Earth. So if you want to get more local data, they do need some downscaling techniques, of which there are many. Some of them are listed here. These are the ones that are available on that website. We used for this presentation, we used the bias correction spatial disaggregation approach, but more recently we've moved to the LOCA data, localized constructed analogs. They all have their strengths and weaknesses. The reason we've moved to LOCA in more recent times is that it's supposed to be a little bit better with more extreme rainfall situations than the other methods, but all of them still have their problems. But the idea here is to get spatial and even time downscaling, so you can get a local data set, reasonably local in any event, on a daily time step. There are over 30 GCMs. I'm not exactly sure the exact number. It depends on which projection or you're looking at, or which set of assumptions. And these GCMs all give different results. And there is absolutely no way to know which one is better than another. So the general thrust of what people decide to do is to use a number of them. They call them an ensemble of models. And then you take a look at what they're all saying and draw your own conclusions. Or you can use them all and do the same. If you use them all, of course, you've got a lot more work to do. Sometimes that's okay, and we've done that. But other times you can drop it down. In this case, we used only 9, but we did check the results against using all 32 on a number of key parameters and found very, very little difference. So somewhere around 10, you begin to get a pretty good estimate of the range that you can expect across the various global climate models. So you don't necessarily have to use them all. If you want to select a subset of the total, say, let's say 10. There are various ways of doing that. One of the methods that we have applied recently is the following. What you want to do really is to see if you can eliminate some of the more bizarre climate model results, and also to try to figure out which ones best match your local data. So here's a step-by-step procedure that we've applied elsewhere that could be helpful. You have to take, in this case, the LOCA data we used. You would take all 32 and you just figure out what their annual and seasonal average precipitation results are. Then you take a look at the current period, let's say 1995 to 2019 or whatever period you want. And then you take a projection period. Let's say you want to look at the end of the century, 2080 to 2100. You rank all of the GCMs and you see what their projected change is between the current and the future time that you're looking to project. And you'll see that some of them will project a very low increase. Some of them might even project a decrease in precipitation. Others are a very hefty increase. I'll show you some results in a second. You'll see how widely they vary. And then the idea here is to try to eliminate the outliers. So in this case, if you take the three smallest projected increases and the three largest, and you discard them as outliers, that's sort of comparable to the 10th and the 90th percentile. You have the remaining, let's say, 27 or 28 models. Then you rank those against what your gauge data says. So in our case, it was the Philadelphia gauge. We say, all right, how does the annual results of the ensemble of, for each model match up against the gauge data? And then you choose the 10 that do the best at matching that annual average. And then you've got 10 models that you would then use in your subsequent analysis. So that's a way of doing it. In fact, in Philly, we did not do that, and that was for a more prosaic reason. There had been an earlier study by the Office of Sustainability, and they had selected 9 global climate models for doing their analysis, and the Philadelphia Water Department wanted to continue or at least match what had been done elsewhere in the city, so we used the exact same 9 models. We did take a look at whether those 9 models would give comparable results that if we had used all 32, and we found that they did. So we were kind of happy with the 9. We didn't foresee any real problems with that. Then you have to go and choose your grids. These are the 4 that we chose that cover most of Philadelphia, and then you would average over those 4 grid cells. These grids are about 12 by 12 kilometers, and that is the output that we had selected. There's some more recent output from the LOCA that actually would subdivide these grids again into 4 and have a much tighter resolution. But for the analysis that I'm presenting today, we use these 4 grids. And then, of course, you need a gauge. Philadelphia has over 30 gauges that have 15-minute data. But for most of the analysis, we use the longer-term results, hourly data from the Philadelphia Airport gauge. And all of the results that I'll be showing you today are based on that particular gauge. You want as long a period of record as possible. And of course, in Philadelphia, that was the airport gauge itself. Remember that the Philadelphia gauge is hourly. The Philadelphia Water Department network has 15-minute data, but the global climate models will only give you daily output. So you're going to have to do some work to get your future projections. Okay, one word here about creating means out of the ensemble that you have chosen, in our case, 9 models. When you first think about it, you would say, all right, why don't we just dump all of the data from the 9 models into one data set and calculate means? This is not a good idea. You'll see on the left that I've just printed a bit of a table, GCM1, GCM2, GCM3. Those are different models. And you see they have daily dates starting from 1950. January 1st, January 2nd, January 3rd. And what you'll see is that some models on January 1st, 1950 didn't predict any rain, and other models did. In essence, they all produce a daily time series, but their storms all occur at different times. So if you average across the 9 models, right away on a daily basis, you're going to get complete nonsense because you're going to be averaging actual days with rainfall with dry days. So the key here is that you must do all of your work in terms of the particular statistic that you're trying to calculate, first individually for all of the GCMs, and then average once you've calculated that statistic. So on the right, for example, we would be calculating the total annual rainfall on a year-by-year basis within each model. Once we have each of the 9 annual average total precipitation, then you can average those across. So you can see, for example, in 1950 on the right, each of the models gave a slightly different number. If you average them, we came out with 43.5 inches. So that's very, very important, but you'll see it quickly if you try to do it any other way that it doesn't work. Okay, so the big question is, can we use this GCM daily output? They are available for the time period 1950 to 2099 from over 30 models. Ideally, you would be able to use them directly and maybe downscale them in some fashion using a statistical downscaling technique to create whatever time step you need, hourly, sub-hourly, and so forth. And people do that all the time. You can do it in a number of fashions. You can create a statistical profile to transform them. This is fairly complicated, but people do it and get reasonable results. Other people use a cascade approach where they subsequently successively split each time step. So you start with a day, and then you take half day, and then you take 6 hours and so forth, and you use a distribution with each time step until you get down to the hour or whatever that you're looking for. We looked at a lot of these, and none of them really provided a time series that looked even close to what we were actually measuring out at the Philadelphia. So we weren't happy with these, aside from the complexity of actually doing them. So let me show you why that is. You're looking now at a screen that shows the average annual precipitation over a period 1950 to 2015. The blue line in both the upper and the lower graph is the actual average annual, the precipitation totals for each year between 1950 and 2015 that we measured at the Philadelphia airport. You can see they're quite variable. They range anywhere from about 29 inches for one year back in 1965 to a very high year of over 60 inches, I think in 2011. And then the top graph happens to be one of the global climate models, in our case, number 4, and the bottom was number 9. And the red line in the top one is what that particular model predicted on a year-by-year basis, and this sort of tan line on the bottom is what global climate model number 9 predicted on a year-by-year basis. And there are a couple of observations here. One, both of those models do show a fair amount of variability year by year, perhaps not quite as great as the actual rain gauge, but not too bad. But the other thing to notice is, if you look at the top in the graph, you'll notice that the wet years and the dry years from the models don't occur in the same place. GMC 4 might have a wet year in, say, 1983, where that might be a very dry year in GMC 9. So they have completely different time series, and they again don't match up with the Philadelphia gauge. So this can create some problems. Now the purple line in both of them is if you do an ensemble average, and you can see that what that does is simply flatten out the variability quite a bit and make a bit of nonsense out of the annual average. You lose a lot of the variability, and you can't really use that ensemble number. So that's a real problem. But you can see that the GCMs do reasonably well on an annual basis. Philadelphia gives you about 42 to 43 inches, and the GCMs do the same. So model by model, they're pretty good at the annual average. They do a little less well on the extremes. This is a similar diagram here, blue being the Philadelphia gauge, and then the red and the tan being the individual models. And again, you can see that the wettest year in Philadelphia, 63, none of the models approach that. The driest year is 29. None of them actually get down that low either, but the table on the left does show the range. It's not too bad, but it does flatten out a little. And again, the purple line shows that if you do an ensemble average, they cancel each other out, of course, and you end up with a useless ensemble average. But if we move to the daily, this is where the problems begin to really raise their head. Again, the same two models, the blue line being the Philadelphia gauge. In this case, what we're doing is we're averaging all of the wet days across that period of time, that 20-year period of time, or in this case, 1950 to 2015. And we're saying, all right, what is the average of the wet days in terms of the intensity or the amount that falls in those days? And if you look at the Philadelphia gauge, just taking that number, it's a little less than half an inch a day across all of that period of time. Now take a look at what the JCMs do, whether it's the individual or the ensemble, they're predicting about half that size storm. So they are really under predicting the amount of rainfall that falls in any given day. And this is a real problem, obviously, if you're trying to use this data. But remember, on this slide here, they were actually doing a pretty good job on the average annual. So how does that work if their storms are way too small? Clearly what's happening is shown in this graph. They are overestimating the number of days it rains per year by quite a bit. So if you look at the Philadelphia gauge, the maximum set of rainy days that we found during that period was about 9 days, and the average time it rained is about 1.8 days. If you look at the GCMs, it's over 3 days. So it's raining too much in the GCMs as opposed to what's actually happening. And so the converse of that means the dry spells that actually occur in Philadelphia average about 3.7 days. The GCMs only about 2.3 days. So what we're seeing here is what is commonly called the drizzle effect. And this is very common for all of these global climate models. So what have we learned from this first analysis is if we can't compare GCM output to any gauge in the Northeast or the Mid-Atlantic range, and this is actually fairly common for all of the mid-latitudes, Europe is included. The GCMs do a very good job of annual average and even average seasonal precipitation volumes, and they're pretty accurate. They tend to underestimate monthly, and they grossly underestimate daily precipitation volumes, and they overestimate the number of days it rains and underestimate the dry periods. And they are also very, very poor at estimating the largest storms. So this is a real problem when we're talking about urban stormwater applications. In essence, we cannot use directly the GCM output. I mentioned that it's called the drizzle effect, and this is the problem that we had to address in Philadelphia and elsewhere for urban stormwater applications. But on the flip side, it is all we have to make projections. So we have to figure out how to do this. And I mentioned there are a few ways of doing it. Many people use what's called a simple delta change method, where they will take a precipitation gauge and they'll ratchet it up by a percentage applied across the board. But we found that this, although this is not a bad technique and is commonly used, it does have two problems. It ignores the variability by storm size and by season. I mentioned that cascade approach or statistical regression approaches people use. Both of them can be done. They're a lot harder to do than what I'm proposing, and I don't think that they give as good a result. So we rejected those in Philadelphia as well. But these GCMs do indicate the change in precipitation is coming, and we need to deal with it. In our case, if we just look at annual averages, the models do predict an increase of about 9% between now and 2080. And the daily average is predicted to go up 10 and the daily maximum by almost 13%. So we need to deal with this in some fashion if we're building things or in the collection system or even preparing for future flooding. All right, so here's some of the results that we had if we looked at the GCMs of our 9. This is a fairly complicated graph, but what it's showing here is a couple of things. If you look on the left, what you're seeing is the percentiles. So 100th percentile means that 100% of all the storms are less than that particular number. That's the greatest storm. And as you go down, 98% of the storms are less than that number and so forth. And down at the bottom, you're looking at the small storms, the 10th, the 9th, the 8th percentile. In the tan is the average across all of the models on an annual basis. And you'll see something very interesting. You'll see, for example, that the larger storms are projected to be increasing about 12%, and the smaller storms less than 1%. This is really, really important. But I also have in the various colors here the various seasons, and you can see again that here is a change as well. All of them show the same pattern. Larger storms are predicted to increase more than smaller storms. But by season, those percentages can vary quite a bit. So you can see on average in spring, a 21% increase for the largest storms, and only about a 4% in summer. But also look at the min and max. The min and max represents the maximum and the minimum of all of the 9 GCMs. And you can see how ridiculously wide these ranges could be. Just look at the tan again and look at the 100th percentile. You can see that the 1 GCM actually predicted that the largest storm between now and 2080 would decrease by 12%, and another one suggested it would increase by 60%. So this is the kind of variability and uncertainty that you're going to have to deal with, and it's something I'll talk about in the second webinar a little bit. But it's clearly something that suggests that you need to use more than one model, because otherwise you have no idea what, which model to choose. They show a wide range of possibility. No one model is necessarily better than the other. We need the ensemble, and you can see that there's a clear difference by storm size and by season. So these are very, very important conclusions. So what is the objective of what we decided to do in Philadelphia? We needed to project hourly precipitation for H&H modeling. We wanted to be able to produce intensity, duration, frequency curves for design. But the time series needs to match local conditions. We already indicated we had to use an ensemble, and we wanted to explore the variability. So what's different? We don't directly use the GCM output. We use GCM output to derive percentages increased by storm size and by season, and then we apply these to an actual time series from the Philadelphia gauge. So here's how that works. We mentioned that the first problem was unrealistic precipitation patterns. So it's not possible to downscale to hourly or 15-minute directly. But also, again, we need this ensemble. So this is the way this worked. It's a couple of fairly simple steps. The first is you take the global climate model output, all 9 individually. And you take the period that you want to use for the current, and you take another period for the future. In our case, we chose 1995 to 2015 period, a 20-year period, and we chose a 20-year period at the end of this century. You sort them by the size of their wet days. So the largest wet day all the way down to the smallest wet day over that 20-year period. You're going to find about 4,000 wet days, and they'll be all sorted according to size. You do that for both periods. Then you align the 1995-2015 with the 2080, and you look at corresponding percentiles. So again, I mentioned the 100th, 90th, 99th, 98th. You just do by a total percentile, and you match them up between the current and the future time period. And you calculate the percentage increase, or in some cases even a decrease, that you might see between those two periods at the equivalent percentile. So the 99th percentile from current. What does the 99th percentile look like in the future? What's that change? And you calculate that percent difference. You will see some odd jumps because of the variability of these models. So we decided that we wouldn't just take that single one that was exactly the 99th or the 98th percentile. We looked at, because we have about 4,000 wet days, we selected the 5 wet days above and the 5 wet days below. So for example, the 98th percentile, might be taking the 98th percentile, the 98th 0.01, 0.02, 0.03, and so forth. That smooths it out a little bit, and we get a percent change. Then we develop a table of those percentile changes by 1 through 100 after we've done an ensemble average of those percents. And it looks something like this. This happens to be spring. So you'll see the average change across the 9 models using this method, and the 100th percentile increases by 21%, 19, 16, and all the way down to the 1 and 2%, where you're only getting the 1 and 2 percentile, you're only getting a 1% change. So again, very, very clearly, the large storms are increasing dramatically. The small storms are not. On the right, you can see the variation that we got across the 9 models, but we use the ensemble average for this. So now we have a set of percentile changes by storm size and by season. And you can graph them. They look something like this. So you can see that each season is a little bit different. Across the x-axis, those are the percentiles, the small ones, 10, 20%. And the larger storms, the 80, 90, and 100%. You can see that they all increase as the storm size increases, but it's different in each season. So some of them increase up to 20%, other ones only about 5 to 10%. So these are the delta change factor distributions that we now have that we can use. Just a note here, originally we were thinking we could use the actual estimated changes in inches per hour or inches per day or whatever, and then we realized quickly that that was not the case. So you need to calculate the percent inches per day change between the current and future, but then turn that into a percentage increase when you are applying it to the gauge data. And the reason for that is quite clear. Remember that the inches per day that the GCMs are producing are about half of what they actually are, so you will be making nonsense of your projections again unless you do it by percentage. So then the step 2, you go over to your rain gauge and you have hourly rain gauge. So you aggregate that up to daily totals so that you can match what the GCMs are doing. You keep the date and time because you're going to disaggregate them later on. Then you rank those daily totals by size the same way, and then you can apply the delta change factors by percentile. So you take the 99th percentile storm or wet day in the Philadelphia time gauge, you apply that percentage that you calculated using the GCM, and so forth, all the way down 100 to the first percentile. Then because you have about 4,000 of these wet days and you're only doing 100 of them, you interpolate in between and you end up with a daily rainfall for 2080, 2100 based on the Philadelphia gauge. And this is what it looked like using the actual storms and the delta change factors that we did. So you can see the black dots are actual storms from the Philadelphia gauge, and then on the left, the delta change factor that was applied to that based on the storm size. And again, this happens to be for winter. You can see that in winter, the largest storms are going up by 20%, the smaller ones only between 1 and 5%. So now we have a 2080 daily time series using Philadelphia, but we've kept the time stamps and the date stamps and so forth. So now you can disaggregate those dailies, wet periods back into the time series, interject the dry periods that you had, and you now have a model-ready, realistic hourly or sub-hourly time series for use in H&H modeling. And this was our goal from the very beginning. And it looks very, very, very realistic because it's based on the Philadelphia gauge, but it's using, to the best of our ability, the percent changes that the GCMs are giving us. So here's a technical note on this. I mentioned wet days. You can also disaggregate the Philadelphias into storms or aggregate them into storms. We did that as well using a interevent time of 6 hours. That means that if it rains for a number of hours, but then you have a 6-hour dry period, if it starts to rain again, that's qualified as a new storm. So you can create storms or you can create wet days to do this analysis. We did it both ways. And the results were almost identical. And the reason for that is that storms in Philadelphia are only about 7 hours on average. And so, except for a few exceptions, most of them don't cross that 24-hour period. So the actual wet days, 24 hours, or the storm approach gives you pretty much the same result. And sometimes it's easier to do it by day. Okay, a few conclusions. The projected change from current to future is not uniform across storm size. This is absolutely important because in many cases you're really looking at the larger storms. It also differs by season, and that might be important for whatever you have to be planning for. The GCM output did not suggest any change in the number of wet days or wet hours across the years. So that's kind of important. Otherwise, you've got to do something a little bit different as well. I'm not going to talk about that today, but in this case, it wasn't necessary. And that's pretty much the case for most of the mid-Atlantic and Northeast region. 2080 shows about the same number of wet days as current. The future increases are thus a result of more intense storms, not necessarily more storms. The delta change method should consider storm size and season. Model ensembles must be used. Statistics should be first calculated for each GCM, then averaged. This is really important. And then delta changes should be applied to real rain gauge data. If you try to use the GCM output, you will get very unrealistic results. All right, that concludes my presentation. I'm happy to entertain any questions in the last 20 minutes. I guess, Corin, you will field them?
Yes, thank you
I will
so
stop
much.
sharing.
Great, and just a reminder, this webinar is being recorded and we'll be posting the video of it on the event page for our workshop. And I'll also be emailing a link to it to everyone that registered to attend. So if you wanted to watch another piece of it again or look at a slide, you'll have access to that probably by tomorrow. So we have a question from Rob Graff. What do you do to estimate whether winter precipitation will fall as rain, sleet, or snow?
That's a good question. We tended to ignore that in Philly because the amount of snowfall is relatively small. I would imagine if you're going to do this further north, you're going to have to address that particular one. I would imagine translating the snowfall into rain amounts, and that's not as easy as it sounds. We haven't addressed that, to be honest with you. It's a good question. I would have to think about that a little bit more. But in Philly, we just ignored that in this particular case.
A question from Tyler, is the delta change factor ever less than 1.0? For example, a decrease in precipitation?
Yes, I think in some of the tables I showed, some of the models were projecting a decrease in the intensity of some storm sizes. Again, because none of us can tell you which model is better than the other, you're going to have to deal with that. And you know, my suggested approach was to throw out, you know, the greatest changes and the smallest changes, and the smallest changes in our case happen to be very large negative ones, and then use the ensemble averages. So we were still left with models that were projecting a decrease, and we simply averaged them in so that our annual average projected increase was smaller than it would have been if we had ignored all the ones that showed a decrease. But I had no reason to question one model versus the other. So, and I don't think anybody does. Yes, you're going to have to deal with that. Some of them do show that.
Does anybody else have any questions? You can type them into the Q&A box or raise your hand and I can unmute you to ask the question.
Corinne, while we're waiting for other questions to come in, this is Franco, I'll ask 2 questions myself. Mark, I'm just curious, the drizzle effect that you mentioned, to what extent does that influence the percent changes in the low amounts of daily precipitation? I would imagine that if the models are overestimating, it's sort of drizzling all the time, that your percent changes. Is it that the drizzling happens in the historical period as well as in the future period, so it kind of comes out in the wash in terms of a percent change?
Yeah, good question. Yes, that's exactly right. So we're kind of at the mercy of these models. So our assumption here obviously is, despite the fact that the drizzle effect is there, the GCMs do provide a fairly wide range of storm sizes or wet day sizes. And so we have to make the assumption that they are going to model percent increases that are reasonably transferable to actual storm sizes by percentile, but that's of course a great leap of faith. But we don't have a whole lot of other options. Now, it's well known that all of these GCM outputs really do a very poor job on the larger storms. So our increase at the top size storm is only anywhere from 15 to 20%. And the prevailing wisdom of a lot of these global scientists, global climate change scientists, is that that's a gross underestimation. So there have been other attempts at using weather models and so forth. And some of those are quite scary. They're showing large storm increases of anywhere from 40 to 70%. So when we talk to the experts in this field, they feel that our method is probably very good up to somewhere in the 90 percentile, so between 90 and 95th. Once you get above the 95th percentile, you'll see some oddities. Some of the percent increases drop a lot for no particular reason, and that's just because the models are not doing a good job. So what we've been doing is we've stopped using the direct percentiles that we calculate anything above the 95th percentile, and we simply take the slope of the delta change factors between the 90th and the 95th percentile, and we extend that up to 100 to avoid some of those nonsense results that we're getting at the high percentage. But there's no real good answer for this yet, Franco. Everybody's working on the extreme end of the scale and trying to figure out what those percentage increases might be.
Right. So on the low end, you have drizzling. On the high end, you've got sort of uncertain conditions with
yes, and poor model model accuracy. The accuracy begins to really drop off above the 90th percentile storms. Right. So one of the things that some people are working on is actually using weather models to try to do this, but the computing effort for that is so great. But there have been one or two attempts at that, and that's where those very high percentage increases are coming from.
Yeah, and we have actually one of those in 2 weeks. We'll have, or the third presentation in this series, we'll look at some weather models. So
okay, that's fantastic, because that's really, right now we're struggling with that aspect of it.
Another question from Keith. You've described advantages to using this form of delta correction, but what are the trade-offs? For example, if the GCM's consensus was that dry spells were to become markedly longer, would that be represented in the scaled delta output?
Yes, it would be, but you're talking about areas not not the Northeast and the Mid-Atlantic, where the dry spells and the wet spells are not projected to be markedly different. But yes, that is occurring in other areas of the country. So you would have to adjust the approach a little bit on that to take advantage, or to take that into consideration. We have worked out a way of doing that, but we haven't used it yet because we haven't had to either in Virginia or in Philadelphia. But yes, if that were the case, then yes, you would have to alter it, because the number of storms and the dry spells would be different lengths.
Question from James. Has the method been written up somewhere? Yes,
we published it in the ASCE journal, the peer-reviewed Journal of Water Resource Management and Planning. That is available from the ACE.
And maybe we can share we can't share the article because of copyright issues, but we can share the citation.
Yes.
And these lists, right?
Yep.
Okay. Yeah, I can send that out to this group as well. Rob, I'm going to unmute you so you can ask your question. Go ahead, Rob.
Hi there. Can you hear me now?
Yes, sorry.
Okay. Sorry, I was looking at the instructions on the screen. Excuse me. A couple questions. First of all, you noted earlier that the cell size that you used were the 1/8 by 1/8 degree cells that are sort of standard for downscaling, and that and I think you used 2 cells for Philadelphia. You also
we used 4 actually, but
4. Okay, gotcha. Sorry. You noted that, but you averaged those 4 cells together. Is that correct?
Yes.
So if you had further downscaling, as you noted, you could get up to 16 cells, if I believe you're right with
yep.
if I recall correctly. And those cells might fall in different drainage sheds of the city's drainage system. Would there be any value to keeping those disaggregated, or is the purpose of averaging them just to I guess, at what point does the downscaling actually become useful at providing spatial resolution, and at what scale is it not? Because there's clearly a difference between Philadelphia and New York, but is there a difference between Northeast Philadelphia and West Philadelphia, either in the current or the projected?
Okay, good question. It happened in Philadelphia that there wasn't any difference between the four. They all were giving pretty much the same results, so we averaged them. The key here is where your location is. So if you're close to the coast, for example, there could be a significant difference, or if there's some elevation difference in near mountains or so forth, and you have a clear change in elevation, there could be a significant difference. It would be worthwhile not running the analysis in two different grid sizes or two different grid locations. Just keep in mind, because you can get involved in these things. There is kind of a point where it gets ridiculous. If you looked at the variety of projections across the GCMs, I think I showed one that showed a 20% decrease versus a 60% increase. Don't get carried away with locational differences if you're looking at a couple of percent here or there, because then you're kind of you're kind of making a lot of work for yourself within something that's producing a much cruder estimate. If you get what I mean. So there's a little bit of common sense associated with it. In Philly, because of the location, not near the coast, and the elevations were all about the same, we saw the four grids being the same. But I could imagine plenty of locations where there would be a dramatic difference across the area that you're analyzing, or if the area is huge, that you might want to do it 3 times using different cells.
And if I may ask one more question, not related to that, but this essentially assumes that or maybe it doesn't, about whether the storm duration is going to be the same in the future as it has been historically. I'm thinking, for instance, if you have a 3-inch or 4-inch storm, and currently that falls typically in a, say, 4-hour period at a rate of 1 inch per hour, would this method resolve whether that might be a 2-hour storm which produces 2 hours of rain per hour in the future, or is that sort of not within the capabilities?
The method right now does assume that the general storm durations are going to be roughly the same. We came to that conclusion because that's kind of what the models were doing. They didn't show an appreciable change in the duration distribution in 2080, 2100 than the models produced for our current period. So we felt reasonably comfortable with that assumption. Again, it's something you should check depending on where you are. I think if you checked it in most of the Northeast Mid-Atlantic, you're going to find that that's the case and you don't have to worry about it. But there might be certainly areas where that is something that you would have to consider, in which case you'd have to do something extra in terms of your future time series that you're applying the percentage increases to.
Great, thank you.
Okay, a question from Tyler. When applying your method to the full PIA time series, how does the total annual change compare to the annual change in the GCM ensemble?
Say that again. I'm not sure I understand the question.
When applying your method to the full PIA time series, how does the total annual change compare to the annual change in the GCM ensemble?
Well, as I mentioned, of course, we're applying the percent change. So the percent change will be identical because that's what we're applying to the Philadelphia gauge. In terms of the total amount change, using putting the percent against the Philadelphia gauge data will produce a much larger increase in total volume than if than the models are predicting because of the drizzle effect. In other words, their storms are half the intensity that they should be. So when you increase a storm of half the intensity by 50%, the actual increase in terms of amount is much less than if you're increasing by 50% a storm that's twice as large. So yes, the total volume on the Philadelphia gauge goes up quite a bit, but that kind of is at the heart of our contention that you have to use percentages and use an actual gauge, because otherwise your volumes are going to be way off. Does that answer the question? I think I've understood the question.
Tyler, if you needed more clarification, you can either type it in or raise your hand and we can unmute you. He says yes, that answers it.
Okay, great.
Francisco asks, can the delta change factor be combined with existing IDF rainfall depth similar to the daily rainfall data?
I'm going to be talking about IDF curves in the next webinar. But yes, the advantage of what we've done here is that you can literally create IDF curves with your future time series, because you've created a time series that's hourly for 2080, 2100. That's very, very similar, well, as variable and as similar to actual Philadelphia gauge. You can actually generate an IDF curve. You don't have to try to shift it by some percentage based on an annual total, which is what a lot of people do. They just shift them upwards. You can actually recalculate your IDF curves using the time series that you've created. I'll talk a little bit more about that next week, along with the stochastic weather generator that goes along with this approach that helps us to understand a little bit the potential variability of these things.
And I can send the link to register for that webinar in the follow-up email from this webinar as well. I know a lot of folks did register for both, but in case anyone didn't catch that link, I'll send it again. I don't see any questions right now, so we still have 8 minutes left. If anybody wanted to ask any more questions, we have some time.
And I can jump in with one more question.
Mm-hmm.
This is Franco. So I know the way you did this with Philadelphia is you ended up picking the models that the municipal government wanted to use, but you outlined before that sort of a procedure for selecting, for example, 10 out of the 32 models. And if I understood correctly, the procedure involved looking at the present day period gauge data and comparing that precipitation to the models and picking the models that sort of seem to be within a certain error threshold of today's precipitation. And then you stick with those models. But the question is, and I don't know, maybe it's an unfair question because it's more of an atmospheric sort of climate question, but is that sort of validation process using present day conditions, does it fall short not knowing, since future climate is going to be, it seems somewhat dramatically different than it is today, I guess it's possible that the models the GCMs that most, closely fit present day precipitation could deviate widely from what we're ultimately going to get. And so therefore, and I know that that's pretty much the best you can do because you don't know how much it's actually going to rain in the future. But I'm just wondering if you've, in this work, if you've sort of compared notes with some sort of climatologists or others who might be able to, who may have told you something about that question.
I haven't directly compared notes, but this method is one that other people have used and published or presented. You're right. You're at the mercy. Who knows what it's going to be like in the future? The one word that I would say is I happen to say this approach, which we're using down in Virginia. You can look at how well they match up on any one of a set of statistics, that you can choose, and the list of ones that, that match the best will change depending on which statistic you use. So you should, in any event, decide on comparing them with the gauge data on the statistic that you're most likely or most interested in. So if it's an extreme value, you might say, all right, which ones have done the best job in modeling extreme rainfall? Or if you're looking at a water supply plan where the annual totals is more interesting, or seasonal total, you might rank them based on their ability on that particular seasonal total. So you have a choice there. But the key concept, and I said, is I haven't really dreamed this up, other people have done this similar kinds of things, is to think about a little bit throwing out the weirdest ones in terms of their projections on the statistic that you're most interested in, and then using to the best of, of your ability, matching up with recent data. And again, depending on what statistic you're most interested in, the method could change a little bit, but it's really all we've got.
Yeah, no, I appreciate that. What made me think of it was when you were saying the thing about the extreme precipitation, kind of throwing those out, and that the uncertainty builds when you talk about extreme precipitation.
Yeah.
The future is expected to be characterized by more extreme precipitation events. It sort of struck me that the GCMs that are better at, sort of simulating the physics of those cloud bursts might not be the models that were good at, sort of routine precipitation that's historically been the case. So
that's a very good point. And for that reason, you might attempt to take a look at how well they do their extremes, even though their extremes aren't quite up to snuff. But I don't have any other ideas on that. So.
Yeah, no, it's not an easy one.
Yeah, it's not an easy one.
Sorry, a couple more questions came in. Abdul asked, will a recording be made available for future referencing? Abdul, I'm assuming you mean for this webinar, and yes, this webinar is being recorded, and I will send a link to it to everybody that registered, and we'll also post it on the event page. And then another question is, how much effort in hours and or money would be needed to apply this methodology to another location?
I mean, it's hard in absolute terms to say. One of the reasons we came up with this method was because it's not all that difficult. Most of the work was done in R programming. Well, certainly our company now, Philadelphia Water Department, has those R programs. So, redoing it is very, very quick. We're doing it down in Philly, and I'm down in Virginia. I think we're spending maybe 150 hours, something like that, with somebody who knows what they're doing. So it's not a huge effort. It's a lot easier than a lot of statistical methods that are being done elsewhere. And that was part of our goal here, is we thought, okay, there's got to be some sort of practical application here for smaller municipalities or utilities that simply don't have the resources or the time. But I also personally think that the method gives almost better results than a pure statistical one, even though it might not answer some of the questions that, like Franco is posing.
We have one more question. This might be our last question because we're running close to time. A comment regarding Franco's question. From what I understand, you still want your GCMs to match the past when you run them back in time. This means that they are capturing the physics correctly. The future non-stationarity should come from the climate forcing from the different emission scenarios. Yes, the GCMs are not perfect and are not capturing the extremes, but the only way we have confidence in them is seeing how well they replicate the past.
Yeah, thank you. That's helpful.
Yep.
Okay, well, we have just a minute left, so maybe we should wrap up.
Yep. So thanks to Mark for giving us a really insightful presentation, and we're looking forward to the next one, which is at this same time next week. Thanks to all of you for joining us, and we hope you enjoyed this. We hope you join us for the next one, and we hope that you have access to the event page for the actual workshop, the in-person workshop that we'll be doing in the beginning of March in Washington, D.C., where we really want to roll up our sleeves and talk to all of you and sort of develop a new set of sort of feelings on the state of the art of what we can do and how we should do it. And so I think this was a great kickoff presentation. So thanks very much, Mark.
Oh, my pleasure. I hope it's helpful to people.
So with that, I guess we will call it the end, and look forward to talking to you next week.
Great. Thank you.
Thank you,
everybody.